Okay, Bismillahirrahmanirrahim. Assalamu alaikum, and welcome back in General Chemistry lectures. Inshallah, today I'm going to complete Chapter 11 with you, which is entitled Liquids and Intermolecular Forces. We have already started last lectures. Inshallah, let me start with sharing with you the file. I'm going to use it. Okay, that's it. Okay, that's great. Okay, Chapter 11, lecture number 2. Chapter 11 is discussing liquids and intermolecular forces. And inshallah, this will done by me, Mahmoud Abdel-Latif, under the Department of Chemistry, College of Science, United Arab Emirates University. Last time we have reached to that slide, which discussing the behavior of the boiling point with the some groups. Just reminding you, just revising it with you. Okay, these are some compounds for group 7 and group, let's say, okay, hydrogens of group 7 and group 6 and group 5 and group 4. And okay, just let us start with group 4. Okay, this one. Okay, actually going from here to here, the molecular weight increases, and actually all these compounds are non-polar compounds, so you could expect and conclude that the only intermolecular forces between the molecule is London dispersion force, which increases with increasing the molecular weight. And actually this trend is normal without any anomalies, without any strange behavior. Okay, just going to higher groups 5 and 6 and 7. Let us, for example, start with group 6, say to say, okay, which contains oxygen and sulfur. Oxygen, this is H2O, and this is H, okay, 2S, okay, and this is H2SE and H2TE, okay. Going from oxygen to sulfur to Se to E to Te, the molecular weight increases. You could expect that the behavior should be in this direction, okay, but there is anomalous for the smallest molecule, which is oxygen. And okay, so it's from sulfur to Se to Te, the behavior is normal without any strange behavior. Well, the strange behavior came for the oxygen, the smallest molecular weight, which is water. What's the reason for that? Actually, we agreed together the London force is found in all compounds, but for hydrogen, there are another very strong intermolecular forces. Inshallah, I'm going to discuss it with you today, which is hydrogen bonding. Actually, water is a highly polar solvent, so dipole-dipole interaction is strong, and this dipole-dipole interaction is promoted to hydrogen bonding. Okay, so the polarity cause a very okay, dramatic anomalous in the behavior and increasing the boiling point. Okay, so increasing the molecular weight, increasing the molecular increasing the boiling point. Okay, as you see, this is boiling point. Okay, so the higher value of boiling point of water is attained to, okay, to the hydrogen bond. The same behavior in this group happens in group okay 7 and okay, group 7 and 5. 7 and 5. Okay, the same, the trend is normal from this is fluorine, and this is HCl, and this is HBr, and this is H iodide. Okay, so the trend is normal from chlorine to iodine, increasing the molecular weight, increasing the molecular weight, increases the boiling point. while the anomalous comes for the HF, the smallest molecular weight compound. The reason for that, fluorine has the highest electronegative atom in the periodic table. This compound is very, very polar. It's a strong polar compound. It has strong polarity and also is promoted to hydrogen bonding. So these are the reasons for increasing the boiling point for hydrogen fluoride. The same happens for nitrogen NH3, this one, NH3, and this is phosphorus H3, and so on. So the behavior is it's normal from phosphorus to SP, while anomalous came from for the ammonia in H3 due to the polarity of these ammonia compound. So in non-polar compound, the only intermolecular force are London force, okay, while for the polar compound there is another force which is hydrogen bonding, which is the main reason for increasing the boiling point for these compounds. Okay, now let us discussing the hydrogen bonding. What is hydrogen bonding? Okay, and just simply hydrogen bonding from its name, it's electrostatic attraction between the hydrogen and the more electronegative atom. The more electronegative atom, especially you could discuss with oxygen and fluorine and the nitrogen. So first of all, these hydrogen, okay, which attracted to the more electronegative atom, it should be in the first place bounded to higher electronegative atom. It should be bounded to higher electronegative atoms, so it can form a hydrogen bonding with another more electronegative atoms. Okay, this kind of electrostatic attraction is called hydrogen bonding. Okay, and just reminding you, these are covalent bonds, intramolecular forces, and the red dotted line is intermolecular forces, and in that case it's hydrogen bonding. Actually it's a dipole-dipole interaction. Okay, these are water, okay, as you know, which is polar compound, and here it's partially negative, and here it's partially positive, and a partially positive. Okay, if you have another molecule of water in that one, this is partially positive. The interaction between this negative and positive charge, this is dipole-dipole interaction. Once this dipole involve interaction between hydrogen and any more electronegative atom, it's called the hydrogen bonding. Okay, so hydrogen bonding, it's dipole-dipole, while once it has a hydrogen attracted to a more electronegative atom, it's called the hydrogen bonding. Okay, so the dipole-dipole interaction experienced when hydrogen is bounded to nitrogen, and the oxygen and the fluorine are usually very, very strong. We call these interaction as hydrogen bonding. Okay, hydrogen bonds or hydrogen bondings. Okay, the same. Okay, these kind of dipole, as you know, this is a vector quantity which is directed to the direction of pooling of electron, and fluorine and oxygen and the nitrogen are more electronegative atoms, so the pooling are towards them. Okay, and this, as I mentioned, this is hydrogen bonding, and this is hydrogen bonding, and so on. Hydrogen bonding is very, very strong interaction. Actually, it's not the most strongest in the intermolecular force. Actually, we have 4 intermolecular forces. The most strongest one is ion-dipole. Okay, ion-dipole, and it comes after ion-dipole hydrogen. Okay, bonding, and it comes after that dipole, and it comes at the end London force. Okay, actually hydrogen bonding is the main reason for some behavior of some compounds, like for example water. Just I'm asking you, just okay, I'm giving you an example. Could you okay, just discuss with me the difference between H2O and against H2S? Okay, this is oxygen and this is sulfur. Hydrogen are the same. Actually, this is at room temperature. It's a gaseous state. It's a gas. Okay, It's a gas, okay? And this is liquid. Okay, the main reason for H2O to be liquid and the main reason for H2S to be gas are the intermolecular forces between the molecules, okay? Oxygen is a highly electronegative atom, so this compound contains hydrogen bonding, and this does not contain hydrogen bonding. So you could expect that the boiling point of that one is very, very high compared to that one. And I have already showed you in the previous lecture, and in the start in today's lecture that, okay? So the main reason for substance to be liquid, to be a solid, are the intermolecular forces. In case of water and H2S is hydrogen bonding. So hydrogen bonding arises apart from high electronegative atoms like nitrogen, oxygen, and fluorine, okay? If you look to this diagram, okay, this is water molecule, and this is intramolecular force, and this one intermolecular force, which is called hydrogen bonding. There are three types of the hydrogen bonding: strong, okay. Inshallah, I will discuss it later in physical chemistry too, I think, or might be in your research. Inshallah, if you're interested to do some research in the future. Strong and medium and weak hydrogen bond, okay. And these types depends on the distance between the bond length of hydrogen bonding, and also the distance between the heavy atoms, okay. The distance between the heavy atoms, here it's oxygen and oxygen, okay. The hydrogen bonding, it's bond here it's 1.8, and it reached to something 2.4. This is weak one, so to say, and this is strong one. As the distance between the hydrogen and the electronegative atom decreases, the strength of the hydrogen bonding increased. Okay, here the dotted line, red dotted line, are hydrogen bonding, as you see, and it's responsible for many anomalous behavior of water. Inshallah, I'm going to discuss today with you. And also the star shape, the responsible for the star shape is the hydrogen bond. Okay. Also, when hydrogen is bonded to one of those very electronegative elements, oxygen, nitrogen, fluorine, the hydrogen nucleus exposed to form hydrogen bonding with another more electronegative atom. Okay, these are some examples. Another example, this is water molecules. Okay, it's dipole-dipole interaction. Once it involves hydrogen, it's called hydrogen bonding. This dotted line. Okay, this water. Problem, the same. Ammonia also form hydrogen bonding. Hydrogen fluoride also form hydrogen bonding, and this kind of hydrogen bonding between nitrogen and hydrogen. And this hydrogen is bounded in the first place with electronegative atom. There it's nitrogen. Okay. Also, this one, it's a hydrogen bonding between the hydrogen which is attached to nitrogen, and which is electronegative. Okay, which is attracted to more electronegative atom, which is oxygen in that one. Okay, hydrogen bonding, as I mentioned, it is responsible for some anomalous behavior of water, especially of water. For example, let us discuss with you the liquid. You have agreed together liquid and solid are condensed phases. Okay, solid are condensed phases. So, can anyone answer me which substance is the more dense? The density of solid is higher than liquid or smaller than liquid? Can anybody answer me the density of solid? Ms. Fatima, are you there? Ms. Khalifa, Mr. Khalifa.
Doctor.
Habibi, are you there?
Yes,
okay,
I am.
Great. Okay. Can you answer me which has higher density, solid or liquid? In general. Okay, forget about it. Actually, in general, right, you are right. Solid has higher density than liquid. This is in normal conditions, okay? While when you came to water, you will find that ice, which is solid state of water, is of lower density than liquid water. Subhana Rabbil Azim. And the main reason responsible for that is hydrogen bonding. okay? And this is okay. Subhana Rabbi, if the opposite is happen, okay, all the living organisms in oceans and seas and rivers will die, okay? So ice is floating over the surface of the water, okay? Hydrogen bonds are responsible for the floating of ice. In general, solids are usually more closely packed than liquids, so it's a higher density, therefore solids are more dense than liquids. Ice has the opposite behavior. Ice is ordered with an open structure to optimizing the hydrogen bonding, which is responsible for increasing the volume of the ice, and that's why its density decreases, because density is equal to the mass divided by volume, and the volume of the ice is greater than the volume of the liquid. That's why the density of the ice is lower than the density of liquid water. Therefore, ice is less dense than water. Okay, this is open structure for the water. As you see, it's arranged, and the optimization of this hydrogen bonding. You could imagine that. Could you imagine if you put something in the freezer, it becomes very tough. Okay, the same hydrogen bonding you could imagine it's become tough. That's why it keeps the molecules away from each other. That's why the volume increases. So optimization of the hydrogen bonding, it's arranged in a certain way, which increase the volume, which increase, I mean the hydrogen bond, which increase the volume, and that's why the density decreases. So you see the ice float over the surface of the liquid water, and also in this diagram, this picture the same. Okay, just summarizing the intermolecular forces and how can you know which is which. How can you determine the type of the intermolecular forces inside the mixture you have, for example. To know that, just ask yourself a question: are ions are present in the mixture? Yes or no? If it's yes, you have ions. Okay. Just ask yourself another question: are polar molecules are present with that ions, like for example water? If it's yes, so you have ion-dipole interaction. Ion-dipole interaction. Okay. If you have only ions and you have no any polar, okay, so you have ionic compound. You have ionic compounds. Okay, ionic compounds. Okay. So in the first question, when you ask yourself if ions are present, there is no anions. Okay, so you have in your mixture polar. If you have a polar compound like water, if you have a polar, ask yourself another question. If you have a polar compound, are polar molecules are present, so you have dipole-dipole interaction. Okay, before dipole-dipole interaction, okay, you have dipole-dipole interaction here. If the dipole-dipole interaction involve a hydrogen atom, okay, so it's a hydrogen bonding. Sorry, if it's involve hydrogen, yes, it's a hydrogen bonding. If it does not contain hydrogen bounded to nitrogen and oxygen and fluorine, so it's a dipole-dipole interaction. Once you ask yourself, once you know there is no inner ions, okay, and you ask yourself, are polar molecules are found? If it's no, no polar compounds are found, so you have only random force. So you have compounds which are non-polar, so it contains only random force, which depend mainly on the molecular weight of that compound. Okay, so these three are called van der Waals, okay, van der Waals forces, dipole-dipole dispersion, and also hydrogen bonding. If you go from here to here, increasing the strength of the intermolecular force. I told you the most strongest one, okay, ion-dipole, and it comes hydrogen bonding, and comes dipole-dipole, and in the end, London dispersion force. Okay, great. Actually, as I have already told you in the beginning of this chapter, intermolecular forces are responsible for many properties of the substance. And so we need to discuss, okay, it's affect many physical properties, like for example, boiling point, okay, and also melting point, and also vapor pressure, and surface tension, and so on. Okay, just look to that, compare these two molecules together. Okay, here there are two hydrogen bonds between the molecules, and this molecule can form only one hydrogen bond. So what do you expect? You expect that the boiling point, okay, the strength of the intermolecular forces here is double that one. You could imagine that, okay, or it's stronger than that one. So you could imagine the boiling point here should be larger than the boiling point in that one, okay, as you see, 390, and here 370, okay. If you just read, each molecule can form two hydrogen bonding with neighbors, while here each molecule can form only one hydrogen bond with neighbor. So the boiling point of that one is smaller than that one. So the strength between the strength of the attraction between particles can greatly affect the property of the substance in solution, like inshallah we are going to discuss in few minutes, inshallah. Okay, hydrogen bonding is responsible, for example, for the solubility of some vitamins, and also the reason for for some vitamin to be, they're absent, they're responsible for insolubility of vitamin in water. The most common example, okay, it's vitamin C, which we always use it every day. We are using it in juice and as a fruit and so on. As you see, the chemical structure formula of this vitamin C shows many OH groups. Okay, as you see, you could conclude that this OH or this hydrogen is bound to another oxygen to form at least four hydrogen bonding. So when you this vitamin is mixed with water, it's solved in water due to the formation of the hydrogen bonding between the water molecules. So it's called the water soluble vitamins. And why it's soluble? Because it can form many hydrogen bonding with water molecules. On the other way, in the opposite, okay, on the other way, if you look to vitamin E, okay, as you see, it's long chain hydrocarbon, and it has only one OH group. Okay, it's very small comparing to the huge molecular weight of this compound to form or to solve it in water. So this one, it's insoluble in water because it cannot form hydrogen bonding like vitamin C. Okay, that's great. Okay, C hydrogen bonding or the intermolecular force affects many physical properties like solubility, as you see. Inshallah, we are going to discuss some selected properties like viscosity and surface tension and the capillary action, which mainly depend on the intermolecular forces between the molecules. Inshallah, we're going to start with viscosity. Can you have you asked yourself a question why the dropping of water is looking like that one, and the dripping of honey is looking like in this way? Actually, it's very simple. You can answer that the viscosity is responsible because the viscosity of honey is higher than, or it is greater than the viscosity of water, and the responsible for the higher viscosity here is intermolecular forces. Okay, so why the difference between honey dripping and water drops? The difference, or the main reason for that, the viscosity, intermolecular forces. Actually, viscosity, its definition, the resistance of the liquid to flow. Resistance of liquid to flow is called the viscosity. Okay, it's related to the ease with which the molecule can move above each other, sliding over each other. Actually, viscosity depends in two main factors: the molecular weight, okay, and temperature. Viscosity increases with increasing the intermolecular forces, okay, which depend on the molecular weight, okay, and also depend on the temperature. It decreases the temperature. Okay, if you look to that one, this kind of this lower value, it means lower viscosity, and this higher value, it means higher viscosity. I don't think it's important, this kind of things, but okay, just for your information. So viscosity depends on two main factors: intermolecular forces, okay, which has 4 types, okay, or which are 4 types, and temperature. If you look to non-polar chains like, okay, hexane, heptane, octane, nonane, decane, okay, you see here it's non-polar compounds, and the molecular weight increases in this direction. So you could imagine the intermolecular force increases from up to down. So you could conclude that the boiling point increases from up to down. Okay, here 3, here 4.9, and 5 and 7 times, okay, 10 to the power 4, and then increase to 1 time to 10 to the power minus 3. So the viscosity is depends on the intermolecular forces. For the non-polar groups, non-polar chains, or non-polar categories, okay, depend on the molecular weight, as you see. Okay, actually, viscosity is inversely proportional to the temperature. Increasing the temperature decrease the viscosity. Okay, now let us go to the second property, which is surface tension. Have you seen before this kind of things? You could find, okay, you could see that some insects, okay, stand on the water surface without sinking into the pulp. And also, I'm sure you have seen that if you have steel, a very small steel like nail, say to say, and you put it in in the surface of water slowly, say to say, or you will find it stays in the surface of water. Why? Okay, it doesn't sink. Even the density of iron is very, very higher than the density of water. Something like, I think, might be 9 to 10 times, I think. Okay, even it stays in the surface. What the reason for that? Actually, the reason for that is, okay, the surface tension. If you look to that animal, okay, or this, no, it's I don't know. Okay, you know what I mean? Okay, you can see it's in the rains in water. Okay, the water does not stay in its skin. Okay, somebody is writing to me. Okay, thank you so much. Okay, the water doesn't stay in its skin, and also the reason for that is surface tension. Okay, is surface tension. Okay, surface tension, actually, before defining it, just this I have already discussed. Look with this, liquid in a container. Okay, we have 2 types of molecules: bulk molecules and surface molecule. Okay, the bulk molecule here is in equilibrium. The force, okay, affected on it, or the net force affected in it, equal to 0, because this one, if it's pulled in this direction, it's cancelled by the other one, and this one pulled in this direction, cancelled by the other one. So the net force in the bulk molecules is 0. And okay, in the opposite, in the other way, in the other side, the molecule in the surface, okay, the net force affected on it is not equal to 0. Why? Because it's only surrounded by molecules from downward and no any molecules in the upward. So the molecules downward will pull it to down. Okay, so you at the end of the day, the surface of the surface area of the surface molecule decreases because it's pulling downstairs by the pulling molecule. So you could define the surface tension, the energy to increase the surface area again. Okay, so surface tension results from the net inward force, as I mentioned, experienced by the molecule on the surface of the liquid. Okay, which affected by I mean, the molecules in the surface affected by the, or is pulled down by the bulk molecules. Just read these. On any interior molecule, each force is balanced by the force pulling in opposite directions, which means the interior molecules feel no pull in any direction. While on the surface molecule, there is no upward forces, okay, to cancel the downward pulling, which means each surface molecule feels a net down pull. It's called surface tension, as I told you. Okay, now let us discuss the surface tension and the meniscus and the capillary action. Surface tension, I have already told you, it's the force required to increase the surface area again, okay? And it's arises due to the pulling of molecule by the bulk molecules. Meniscus is the shape of the liquid surface. It could be a U shape, it could be N shape, concave and the convex, I think. Okay, this is capillary action. So meniscus is the shape of the liquid surface, as you see. It could be like in A tube or in B tube, in that one. The the reason for the meniscus to be in that way or in that way are two forces which compete each other. Okay, the cohesive force and adhesive force. The adhesive forces are the attraction between the solid and the liquid molecule, and the cohesive forces are the forces between molecules with themselves. So cohesive forces bind the molecules to each other, while adhesive force, okay, it's bind the molecules to the surface, solid surface. So there are competition between these two, okay? The greater one will be responsible for the shape of the meniscus, okay? If the adhesive force is greater than the cohesive force, okay? So you end up with that one, like U shape. If the cohesive force is higher than the adhesive force, so you end up with N shape, okay? If the adhesive force are greater than adhesive force are greater than the cohesive force, the liquid surface is attracted to its container more than the bulk molecules. Therefore, the meniscus is U-shaped, like water in glass. On the other side, okay, if the cohesive force, the forces between the molecules themselves, are greater than the adhesive, which is the forces between the molecule and the solid or the wall, the meniscus will be downward, like mercury in glass. Okay, this is the real meniscus of water. It takes the U shape, as you see, and for mercury it takes the N shape. Okay, if you look to that one, to this figure, okay, this is water molecule. These dot line are the hydrogen bonding between the molecules, water molecules, and this dotted line, okay, are the adhesive force between the solid glass and the water molecule. If these forces are greater than this force, it will end up with the meniscus like in that shape, U shape, okay? While for the mercury, this is the cohesive forces between mercury atoms, which is greater than the adhesive between this one and water. So you end up with the N shape, something like N shape, this one, okay? That's green. So because the adhesive here is greater than the cohesive, H2 molecule touching glass adhere to the wall more than to each other, forming the concave surface, while on the other side, because in mercury in glass, because the cohesive, okay, this cohesive, okay, is greater than the adhesive, which Hg molecules touching. So Hg molecule touching the glass adhere to the wall less than to each other, forming the convex surface. Okay, convex surface. Okay, the last property I'm going to discuss with you in this chapter, inshallah, is vapor pressure. Okay, is vapor pressure. If you have a container, say to say, like, okay, I'm sorry, I'm very bad in drawing. If you have a container, so to say, which contains a liquid like water, for example, okay, and this is evacuated space. You will find in that some molecules in water has, okay, a greater kinetic energy, which can overcome the force of the surface and escape or convert it to vapor, okay, to go to this evacuated space. Before any, okay, okay, in the beginning of vaporization, you have only evaporization, okay. Molecules with higher average kinetic energy will escape, okay, to this space, and you have vapor molecules here, okay. With increasing time, at some times, okay, this is the rate of vaporization. At some times, you will find some molecules of the vapor will condense and return back to the liquid again. Okay, okay. At some point, you will find that now you have two rates: rate of vaporization and rate of condensation. At a certain point, certain time, the two rates are equal. Rate of vaporization, which equal to the rate of condensation, for example, number 2. Okay, at that point, these areas are saturated with the vapor molecule, and the number of vapor here, it's fixed, because if something evaporates, then the same will condense again. So at that point, the vapor, okay, this vapor in the first plate exerts a pressure above the surface of the liquid. When the two rates are equal, this vapor pressure, okay, this pressure is called the vapor pressure. It's called the vapor pressure. Okay, that's great. Be with me. And this is the figure I have already, okay, showed you. Okay, we have two rates: rate of vaporization, these, okay, rate of vaporization, and in the same time you have some molecules which condense it, okay, which are these, and at some points our two rates are the same, okay. So two rates are the same. So this area are saturated with the vapor, and this vapor exerts a pressure on the surface of the liquid. And when the two rates are the same, okay, this vapor is called the vapor pressure. It's called the vapor pressure. Okay, at any temperature, some molecules in the liquid have enough energy to break free, okay, to escape the surface force and go to the evacuated space. It's evaporization. As the temperature rises, okay, the rate of vaporization increases with increasing the temperature. As the temperature rises, the fraction of molecules that have enough energy increases. Okay, just look to that figure. Okay, this is the average kinetic energy against the number of molecules. This is at lower temperature, the blue one, and the okay, the red one is higher temperature. If you look to the blue curve, okay, actually this the of kinetic energy, the minimum kinetic energy for the molecule to escape to evacuated space. If you measure the area under the curve of the blue one, these are the number of molecules that already escaped. Okay, if you increase the temperature, if you increase the temperature, the red one, okay, the average kinetic energy increases. The area under that red curve, which is the whole area, okay, which these are the molecules that already escaped, okay, it's higher than in the case of the blue one at lower temperature. So the average kinetic energy increases, the rate of vaporization increases with increasing temperature, okay. So blue area, in the blue area, number of molecules having enough energy to evaporate at lower temperature. The red one, okay, and the blue one, okay, the number of molecules having enough energy to evaporate at higher temperature. Okay, this is vapor pressure. I have already explained what I'm going to discuss this figure with you. Okay, if you have a glassware evacuated flask, okay, and you have liquid ethanol here, and just let, okay, here is the pressure is zero, nothing here. If you allow to this ethanol to go inside this flask, at some times, or some molecules which has a higher kinetic energy escape, and okay, this vapor or converted to vapor or evaporates. This vapor exerts a pressure. The pressure here, it has a value. The pressure increases. Okay, at some time system comes to equilibrium, which is called dynamical equilibrium, when you have two rates, the rate of vaporization and the rate of condensation, and they are equal. Okay, at that point we have a dynamical equilibrium, and this area is saturated with the vapor, and the pressure of that vapor at that point is called vapor pressure. It's called the vapor pressure. Okay, so pressure is zero. It increases with time. Okay, molecules molecules leave and enter the liquid are equals, which I mean rate of vaporization, rate of leaving is equal to the rate of entering. Okay, at equal rates, pressure reaches to steady state. The pressure becomes constant, and at that point, it's called the vapor pressure. As more molecules escape to the liquid, the pressure they exert increases. Okay, this I have already told you. The liquid and the vapor reach a state of dynamical equilibrium. Liquid molecules evaporate and the vapor molecule condense at the same rate, okay, which I have already showed you before in the beginning of vaporization. You have only evaporization. At sometimes you have two rates, rate of vaporization and the rate of condensation, the blue arrows, which is small. At some point it reaches, okay, sometimes you reach to the dynamical equilibrium between the rate of vaporization, the red arrows, and the rate of condensation, the blue arrows. Okay, at that point, the pressure here is constant. It reaches to steady state. It's a constant, so it's a vapor pressure. Okay, rate of vaporization equal to the rate of condensation, and here rate of vaporization is greater than the rate of condensation. You have only rate of vaporization. Okay, the vapor pressure. Okay, let us discuss the boiling point. What can anybody define the boiling point to me? Boiling point, it's very simple. It's the temperature at which the vapor pressure of the liquid equal to the vapor pressure of the atmosphere. Okay, so the boiling point of a liquid is the temperature at which the vapor pressure of that liquid, equals to the atmospheric pressure. Okay, equals atmospheric pressure. Okay, that's great. Okay, there is a normal boiling point and non or abnormal boiling point. Boiling point. Normal boiling point and abnormal boiling point. The normal one is the temperature which the vapor pressure equal to that one. The temperature, the vapor pressure of the liquid equal to the atmosphere. Okay, because we have already defined it, the temperature at which the vapor pressure equal to the atmospheric pressure. Okay, look to that figure. It's a relation between the boiling point and the vapor pressure. Okay, temperature, okay, in x-axis, and the vapor pressure for different liquids, diethyl ether, okay, ethyl alcohol, and water and ethylene glycol. Okay, the relation between temperature and vapor pressure for the diethyl ether is the red curve. Okay, it looks like this one, increasing the vapor pressure increase with increasing the temperature. Okay, if you would like to know the boiling point, you should at the value of the vapor pressure which equal to the atmosphere, 1 atmosphere, okay, and draw a line which parallel to the x-axis, So this point, at this point, at this pressure, this temperature is called the normal boiling point. And if you would like to get it, just extrapolate or write a line, straight line from this point to intersect with the temperature axis. This is the normal boiling point of that one. Okay, this is the normal boiling point for diethyl ether, which is 34.6. 34.6. For water, okay, this is water, which is 100 Celsius. Okay, this point in the atmospheric pressure. We mentioned that the temperature at when the vapor pressure equal to the atmospheric one. Okay, if you write a line, it will be at 100. Okay, I'm sure all of you know about the pressure bands, which are always in your kitchens, and all people are using it for cooking foods, which cooks foods very, very fast. The main idea for that, it's packed in a way that the vapor pressure of the liquid inside increases, so the boiling point of water increases. So instead of boiling at 100, it boiling, for example, at a temperature greater than 100, and so the food is cooking very, very fast. Okay, so okay, so increase the pressure above the water surface, its boiling point increases. If you decrease the vapor pressure above the surface, boiling point decreases. If somebody, okay, if you go to a higher altitude, okay, if you are, I'm sure all of you have used the plane and traveled to some places when the pilot is going to the upper altitude, you will find some pains in your ears. The main reason for that is the pressure. Okay, if you go upstairs, higher altitude, the pressure decreases. Okay, the pressure decreases. Okay, that's great. Are you with me? Are you there? Ms. Fatima? Mr. Khalifa? Okay, I'm happy. Okay, now let us do some practice. I have already finished what I have, okay, for this chapter, and these are some multiple choice questions. Okay, which force below the strongest intermolecular force? Okay, I have already arranged you before. Okay, the strongest one is ion-dipole, and it comes hydrogen bonding after, and comes dipole after. At the end is London force. So the strongest one is ion-dipole one. Okay. Okay, I could ask you, name the intermolecular forces, intermolecular interactions below. Okay, here I'm giving a chart. The white one is hydrogen, fluorine, sodium, and so on. If you look to that one, for example, okay, this is fluorine, F2, F2. It's a non-polar compound. Non-polar compound, so if it's non-polar, the only intermolecular forces are London force. And we have agreed together London force are found in all compounds. London force are found in all compounds, okay? If you go to another one, say to say this HF, okay, HF and HF, this is polar compound. So it's dipole-dipole. Once it contains hydrogen, so it's hydrogen bonding. So it's hydrogen bonding. Okay, this is sodium, ion, okay, and this is water molecule. So ion and the polar compound, it's ion-dipole, ion-dipole, okay. If you look to sulfur oxide, this is polar compound, sulfur oxide, polar, with a polar one, it's a dipole-dipole interaction, dipole-dipole interaction, okay, which will have the higher viscosity, this one or that one. Okay, this one contains only one OH, and this glycerol 3 OH. So it can form 3 hydrogen bonding. The intermolecular force strength here is greater than this one. So the viscosity here is greater than the viscosity of one propanol. Okay, explain the difference between the boiling point. I have already told you before. This is the molecular weight are the same. So if the molecular weight are the same, just look to dipole and other intermolecular forces other than London force. Here there are two hydrogen bonding between the molecules. This one can form only one hydrogen bond. So you could expect that the boiling point here is greater than the boiling point here because the intermolecular forces here is stronger than that one because the number of hydrogen bonding here is greater than the number and so on. Explain the difference between the boiling point, okay, between these two. Okay, these contains OH, so you could imagine that it can form hydrogen bonding. I told you before the hydrogen that can form hydrogen bonding should be attached to oxygen. So this one cannot form hydrogen bonding, by the way. Okay, this one it can. Okay, so this one contains the London force, and this one contains the London force. This is polar compound. It's ether, methyl ethyl ether. It's polar, so it has dipole dipole, dipole dipole. Okay, dipole dipole interaction. Here hydrogen bonding. Hydrogen bond is stronger than the dipole dipole. So you could imagine the boiling point here is greater than, so it's a big difference between both because hydrogen bonding is very strong comparing to dipole. Okay, propanol has hydrogen bonding plus London force, whereas ethyl methyl ether has dipole dipole plus London force. So hydrogen bonding is much stronger than the dipole dipole interaction. Okay, which force below is increasing in the strength as the molecular weight of the compound increases. The only one which depends on the molecular weight, it's London force, London dispersion force. It's called the London force or dispersion force or London dispersion force. All are the same. So, okay, it's London dispersion force. Which compound below is not capable of forming a hydrogen bonding? This one cannot. It's non-polar. Okay. Okay. Hydrogen bonding is formed between hydrogen and any electronegative atom like nitrogen, like oxygen, like fluorine. So these three can form a hydrogen bonding. This one, which cannot form a hydrogen bonding, so this is the right one. Okay. This is the cannot form a hydrogen bonding. Which compound below has the highest boiling point? Okay, I have already discussed with you in the beginning of this lecture. This is the highest, the greatest hydrogen bonding between those. Why? Because it can form hydrogen bonding. Okay, do you remember the anomalous behavior, which was this is H2O and this is H2S, and there are three here. Okay. Which element below have the highest boiling point? Okay, so once so they are non-polar compounds. So once they are non-polar, so you look to London force. So you look to the molecular weight. As the molecular weight increases, the boiling point increases. So it should be Br2. Okay, it should be Br2. The resistance of liquid to flow is called what? It's called the viscosity. Okay, the resistance of the liquid to flow, it's called viscosity. It's called the viscosity. Okay, the energy required to cause the liquid to boil is called the boiling point. Okay, it's called the boiling point. Okay, at higher altitude. Okay, الارتفاعات العالية. Higher altitude, the boiling point of water decrease or increase. As I told you, if you go to higher altitude, the pressure decreases. Once the pressure above the surface decreases, the boiling point decreases. So if the normal boiling point of water is 100, so it should be less than 100. Okay, it should be that one. These are two examples. Have already solved in details. Just see them, and if you find any problem, just contact me. I'm going to discuss with you. Okay, this figure I have already explained to you. Here I'm asking to estimate the boiling point for diethyl ether at that pressure. Okay, once this pressure is lower than 1 atmosphere, so the boiling point should be lower than this value. Okay, how we can get it? Just you should know this on tour. Once it's drawn on tour, and just multiply it with 760 tall, you end up with 710. So at 710, just write a line parallel to the x-axis, and the point intersection between this line and the curve, it should be the boiling point of diethyl ether. It should be less than this one. It could be 30, for example. Okay? It could be 30, for example. Okay, he mentioned here it's okay. Okay? It could be. This is what is the predominant intermolecular force in that one. This one non-polar compound. Non-polar, so it should be London force. This is okay. Okay. Which one of the following exhibit dipole-dipole interaction? Okay. Dipole-dipole interaction. I doubt for that one. Is okay. I doubt for that one actually. I don't know. This one is wrong. It could be that one. It could be. Okay, but it should be have a T shape, C2 shape. Okay, it could be that one. This one is wrong. Okay. Which one of the following substance has the highest boiling point? Okay, this is 2OH group, and this one OH group, and the other are non-polar. So it could be this one, which contains 2OH groups. This is wrong answer, by the way. Okay. Which one of the following derivative of ethane has the highest boiling point? It's non-polar, so you should see the higher molecular weight, which is C2 iodine 6. So this is the right one. This is wrong answer, by the way. Okay, this is wrong answer, by the way. Okay, thanks God. الحمد لله رب العالمين. الحمد لله الذي تتم بنعمته الصالحات. الحمد لله. We have already finished chapter 11, which is the end of the general chemistry 1. I'm happy I have teach you these kind of things. I'm very, very happy. Inshallah, from next lecture, we're going to revise anything you want in addition to solving the homework for the final exams, the file you have already have. And thank you again, and thank you so much. وجزاكم الله